All right. Hello, everybody. Welcome back to another video. Today, we're going to be talking about Green's theorem and using Green's theorem to compute line integrals. And the problem that we have for you today is from the January 2015 comp exam. It's one that I find particularly challenging in a sense that it's quite different than a lot of the vector calculus problems that show up on the comprehensive exams. It kind of has a unique flavor to it, and we'll explore that a little bit today. So the question is, evaluate the line integral, which is the integral around the curve gamma of y over x squared plus y squared dx minus x over x squared plus y squared dy. So as we can see, the vector field is written in differential form, and it says where gamma is any closed counterclockwise smooth curve, which encloses the origin 0, 0. Awesome. So the way that we would normally go about solving a line integral is to compute it by turning it into a regular integral, right? Using a parameterization of our curve. However, it says here, right, gamma is any closed counterclockwise smooth curve, meaning that while we do know that it is positively oriented, we don't have an exact parameterization for it, right? And when we don't have an exact parameterization, there's not a lot we can do. So the next place that we should turn is to Green's theorem. Green's theorem states that essentially if we have, right, a curve C that is closed, that is simple and connected, right? And we know that our vector field is continuous everywhere throughout the curve or inside the curve, then we can turn this, right, into a double integral, actually, of, I believe, partial q over partial x minus partial p over partial y dA. So basically what we're going to do is we're going to turn it into a double integral across the region of this new scalar field. So that is Green's theorem. But as I generally like to do with these types of problems, I'm going to cross this off because we actually cannot immediately use this, right? Because here is why. If we look at the question, it says that it contains the origin. And when we plug the origin in to this vector field, we see that there's a singularity because we end up with 0 over 0, right? Dx minus 0 over 0 dy. That is no bueno. We cannot do that, right? Green's theorem cannot apply here. So we're going to have to do something else. So let me draw a simple picture of our region. So if this is the origin right here, this is our curve gamma, right? And we know the singularity is right at the origin. So what we're going to do is we're going to create a new curve with a radius epsilon that is oriented counterclockwise, or sorry, clockwise, which would not be that direction. Let me go back. It would be this direction, and we know that clockwise is negative. So we are going to create, let there be, we'll call it gamma 2, which is a circle of radius epsilon. And the reason why we take it to be epsilon is because we don't want it to intersect with our curve gamma. We want it to be very, very, very small. The only thing is that it cuts out the origin, right? And what we can do is we can draw, right, a line connecting it. And if we take the line integral over the whole thing, right, the lines connecting them is going to cancel. They're going to cancel out. And so if we take the line integral of the union of gamma 1, or just gamma and gamma 2, then it's going to create a region that has a hole in it, but that's okay. We can still use Green's theorem. So essentially, what's going to happen is the line integral of gamma union gamma 2 of, and I don't want to write it all out, of f dr, right? we are going to be able to Green's theorem that. That's going to be right over this new region with that little hole cut out in the center. We can find the partial derivative of Q and the partial derivative of P with respect to X and Y, right? So let's do that now. So if we want to do that, right, we have to take the partial derivative of this guy with respect to X and then subtract the partial derivative of this guy with respect to Y. So what is the partial derivative of negative X over X squared plus Y squared with respect to X? Well, that's quite easy to solve. Let's keep this negative out, and then we can just use the quotient rule. That's going to turn into X squared plus Y squared, right, times 1, and then minus, and then that X, right, is going to stay there, but then we're going to take the derivative of the bottom, and that's going to be minus 2x, right? So that's going to be minus 2x squared. And then that's going to be over x squared plus y squared, the whole quantity squared. And then if we subtract that, right, that's going to be, we're going to take the partial derivative of this one with respect to y. So we are going to do x squared plus y squared, right? Plus y squared, right? And then on the bottom, we're going to take the derivative of that, and that's going to turn into 2y squared. So that's going to be minus 2y squared. And then that is going to be on the bottom x squared plus y squared, the whole quantity squared. And basically, what's going to happen, right, is this whole thing is going to go to 0. So basically, this whole thing is going to go to 0. So that's going to become the double integral, right, of 0 dA. And we know that that's going to be 0. So we know that the line integral, right, of gamma 1 union gamma 2, or gamma union gamma 2 f dr, this is going to be 0. Now, we know that we have two separate curves that are being joined. One is positively oriented and one is negatively oriented. So really what this is this is the curve of across gamma of f dr, where r is the parameterization, right, minus gamma 2, because it's a negatively oriented. So instead of adding, we're going to subtract it, of f dr. So essentially, and because this is equal to 0, right, we know that for any curve, gamma, that's going to be equal to gamma of f dr. That's going to be equal to the line integral across this small little circle with respect to epsilon. So we really just need to calculate the line integral across the circle, which simplifies things down a lot. So in order to calculate that, we are going to need to find a parameterization, right, of our curve. So what is that going to be? So parameterize. So to parameterize that, right, we are going to just find the parameterization of a circle, right? So r of t is just going to be cosine t, comma, sine t. And because it has a radius epsilon, we're just going to multiply that by epsilon. So we're going to do epsilon cosine t, comma, epsilon sine t, where t goes from 0 to 2 pi. Right? And then because we're going to need to find r prime of t, right, what is that going to be? Well, the derivative of cosine is just negative sine. That is going to be negative sine t. And the derivative of sine is just cosine. That's going to be, oh, and don't forget our epsilons, epsilon cosine t. And of course, the dt is going to be on there. That is r prime of t. So if we want to evaluate the integral, it's just going to be this, right? So it's going to be f of r of t, which is how we evaluate our line integrals. So that is going to be epsilon, sine t, right? Over, and then epsilon sine squared t plus epsilon cosine squared t, plus, yeah, that is going to be epsilon squared, that is just going to be epsilon squared, right? So that is easy. And then we are also going to have, right, negative epsilon sine t out here. So sine t. So that is going to become, oh, sorry, and because it's a dx, yeah, okay, yep, there's going to be a negative there. And so that's gonna combine. And then we are going to get minus, right? And then up here, we know that we can turn the x into an epsilon cosine t. Epsilon cosine t. And then on the bottom, again, we're just going to get epsilon squared because it's x squared plus y squared, and then times epsilon cosine of t. All right, so now, right, that is going to turn into the epsilon squareds are going to cancel, right? So this and this are going to cancel with this and this are going to cancel. So we're just going to get negative sine t minus sine squared t minus cosine squared t. So that's going to give us, and we know that it goes from 0 to 2 pi. Oh, go back to our pencil. So that's going to be the integral of from 0 to 2 pi of sine squared t negative minus cosine squared t. And I believe that there is a negative in there that should not be there. So let me go investigate and I will get back to you where I did something wrong. Okay, I figured it out. Here's the reason why. Because we are going clockwise. So the easiest fix for that is instead of going from 0 to 2 pi, t is going to be going in the opposite direction from 2 pi is greater than t is greater than 0. So it's going to be going the other way. So in order to fix that, all we really need to do is switch our bounds to be going from, oh, wrong tool, going from 2 pi to 0. And we could reparameterize it with just putting a negative there, but it's actually less work to just do it that way, and I am lazy. But just pay really close attention to that, right? When we parameterize, we need to be parameterizing in the correct direction. So yeah, that's going to turn into 2 pi to 0. And we know that sine squared plus cosine squared is 1, so that's going to turn into negative 1, right? So essentially, this is going to be equal to the integral from 2 pi to 0 of negative dt, right? But because we like to integrate from a lower bound to a higher bound, we can switch that and it'll turn negative. The two negatives are going to cancel out, and that is just going to become the integral from 0 to 2 pi of just dt. So again, you have to be really careful, right? If you are specifying the direction that it is going to parameterize the right way, right? Because two different parameterizations can trace out the same curve, but it will do so in the opposite direction. And as we know for vector calculus, orientation absolutely matters. So what is that going to turn into? Well, that's just going to become, right, 2 pi minus 0, which is just 2 pi, and that is our final answer. So to summarize what we did, And I know that this is quite an involved problem, right? We are going to, instead of finding a parameterization for gamma, because it's a very general curve, we don't have one, we are going to cut out the origin and create this region on which we can do Green's theorem. We see that all of this stuff collapses to zero. Let me highlight what collapses to zero in pink. All of this stuff is going to collapse to zero, and therefore we're able to set the line integral across gamma equal to the line integral across gamma 2, which we know is a small circle of radius epsilon. And so we just find the line integral of that. The epsilons are going to cancel out with our parameterization that we have, and it's just going to simplify down to 1. And you'll notice a very common theme across a lot of these problems that involve vector calculus is that you have these very complicated equations and you have to be really careful which numbers are canceling out with which numbers, right? But eventually you should get something that is relatively simple at the very end, because, you know, the purpose of this is not to evaluate complicated integrals. It is more so learning how to parameterize things and how to compute integrals of vector fields. Awesome. So while this is a relatively complicated problem, I think that it is definitely doable. If you have any questions about it, please feel free to let me know in the comment section below. And as I always say, if you have any requests for problems you'd like me to try out, definitely let me know as well. Hopefully you got something out of this video today and you enjoyed it, and I will see you tomorrow.